Okay, well, hopefully it won't glitch too much. I suspect I haven't done a hard restart on my devices in too long, and that's probably why I'm running into these issues. So we're going to start off talking about linear functions. I feel like every math class you ever take starts off talking about linear functions. So why would this be any different? And in fact, when you get to calculus, you'll do a quick review of linear functions again. You know, it's not nothing too elaborate. In fact, you spend less and less time on linear functions, at least in terms of learning how to construct them. You spend less and less time as the years go on, because it really should be a review. But what we also do is I like to think of it as, all right, you've learned about linear functions in the past, but let me tell you about the favored ones to be using in this class. All right. So we have the slope intercept form, which is y equals mx plus b. The m is the slope, which is the change in y over change in x. And the b is the y-intercept. All right. So that's the tried and true. Most people default to this when they're writing the equation of a line. It has uses specifically when graphing. We like the slope intercept form because if you plot the intercept, the y-intercept specifically, and then count off the slope, rise over run from there, you can get a quick sketch of a graph pretty easily without having to go point by point. All right. The point slope form also has value because that one involves you knowing a point, not necessarily the y-intercept, any point, and the slope of the line. So starting with that given point, you just count off your slope, your rise over run from that location, whether you're going forwards or backwards, doesn't make a difference. But this model is y equals m times x minus x sub 1 plus y sub 1. All right. The m is still the slope. All right. So still computed the same way. So this m is the same as this m is the same as that m. All right. But the x1, y1 is a point on the line. All right. X1, Y1 is a point on the line. Any point. Right. But the thing is, when you're plotting points and making any type of graph, you want to have reasonable coordinates to work with. All right. So yeah, technically 100,000 comma 1,500 could be a point on the line, but maybe I don't want to go out that far. Maybe I only want to go as far as 20, so you want to go with reasonable values that you could select. I see some people coming in. All right. So write the linear equation. So first example, write the linear equation in slope intercept and point slope form. All right, missing a hyphen here, sorry. Given that the line passes through 5, 2, and 7, 9. All right, so we'll start off with the slope intercept. All right, in either case, whether you're dealing with a slope intercept or point slope, you need the slope. I mean, it's part of both titles. So I'll start off with change in y over change in x. It doesn't matter the direction you go in. I'm finding the difference between the y values and the difference between the x values, as long as you're consistent. So I'm going to start with the 2 here and find the difference between that and the 7. So that and the 7, I meant 9, sorry. It's going to give me a kind of a 7. So 2 minus 9. And then I'm going to do the same thing in the same direction with the x's. So 5 minus 7. Could have gone the other way. Could have done 9 minus 2. But if I did that, then on the bottom, it would have to be 7 minus 5. All right. So the direction of the subtraction needs to be consistent. All right. So on the top, I get -7. On the bottom, -2. So that means my slope is 7/2. All right. So now I just need the y-intercept. So there's two ways to handle it. One actually involves you doing the point slope form first, but I don't want to confuse. So I'll just do it the way people are mostly accustomed to. So I'm going to take my y equals mx plus b. I'm going to pop in the m of 7/2, and I'm going to choose one of the two coordinates. Each coordinate is made up of x values and y values. So I have two coordinates here, 5, 2, 7, 9. Each one has an x, each one has a y. All right. The subscripts, when you think about this form here, when I say x1, y1, that's just a designation of which coordinate you're looking for. So, but in this case, what I'm going to do is I'm just going to choose one of the two. And the reason I could choose one of the two is because if you have 2 points and you know that they are on the same line, then it really doesn't matter which one you select, right? Because the x value and the y value will be represented by a point that we know is definitely on the line. And in this case, we know it's on the line because they're saying it's on the line. But sometimes you verify it yourself. You see a line and you just grab 2 points right off of it. But I'm going to grab the first set of coordinates here and plug those in for x and y. All right. So I'm looking at 2 equals 7/2 times 5 plus b. All right. And for this, I mean, you may want to get your technology involved, especially if you don't really love working with fractions. I'm going to make a better quality too here.
Professor, sorry, I have a quick question. The slope, isn't it supposed to be negative?
Is it supposed to be negative? Let's see. 2 minus 9. Well, it's negative over negative, so that becomes positive.
Gotcha. Okay, I was just making sure. Thank you.
No problem. All right. So I have the NumWorks calculator up, but I also have an emulator, if I can ever find it. I have an emulator for a TI calculator. It just doesn't quite. Oh boy, I really messed around with this at some point. Yeah, I don't know where I put it. This is the day for me forgetting where I have everything. And let me see. 84. Just put 84 in. Well, I had an emulator. I'll pull it down at some point. Maybe I could just do it now real quick. It's probably hiding in plain sight, but I have my, what you call it here. First grade, second grade. They put everything for, oh, there it is, graphing calculator 84. I must have uninstalled it at some point. All right. Oh, it was there. Do it like this. All right, so this is the closest you can get in terms of an app that emulates the TI-84. So it's up to you if you want to go this route. You pull down an emulator, or if you get a handheld. You know, eventually, if you're physically in a classroom, you're going to need to have some sort of handheld device. But for now, you can do this, or you could use the NumWorks calculator. Bottom line is, for for most of the stuff we're going to be dealing with, it's simple graphs, maybe a table of values, and simple computations. All right. So there's a lot of online approaches. You could even use the Desmos calculator. All right. But if you're using TI, if you're comfortable with that, then this is fine. It's not exactly the same, but it's close enough. All right. So on the right hand side, I want to do 7/2. Well, 3.5 times 5. So 17.5, and then subtract that from 2. So I'm looking at negative 15.5. My stance on decimals is it's fine. We typically want simplest fraction form, but if you have a clean decimal, like something that you don't have to round, then it's fine to leave it in decimal form. So that's your 0.75s. If you have like a 0.3 repeated, we're not going to write 0.3 repeated. You're going to write 1/3. You know, so using a calculator that'll handle the fractions for you is a good thing. All right. But anyway, I have my b value here. So I now know my equation is y equals 7/2 x minus 15.5, or you could say minus 31/2. All right. I'm going to bring the numworks back in. I'll show you how to do it on that. I mean, you have the freedom to choose which technology you want to use. So, yeah, like you decide and then go from there. Like I said, hopefully I said on Wednesday, I'm gonna show you how to do it on both, because I don't want you leaving this class going into a calc class and then being like, you don't know how to use a TI calculator, you know. So I don't want that to work against you, right? But if you're in the numworks calculator, you just turn it on, and again, you just go to numworks.com and you'll see free online emulator. All right, so you can get it on your phone. This is the app. And I think it's pretty useful as as far as free apps go. So it's worth taking a look at, even if you don't intend to use it. So calculation, and then this is the big operation that I needed here. So 7/2 times 5. When you hit division on numworks, it automatically brings it up as a fraction, which is really nice. Times 5, it gives you the 35/2. Which we got as 17.5, that's fine. But then I had to subtract from both sides. So 2 minus that answer. And we would get not only the fraction form, but also the decimal form. So you can kind of have your cake and eat it too there. Point slope form. We don't really have to go back to scratch here, because we already computed the slope. I'm not going to just pretend that we didn't and like do it all again, you know. So we can jump right to the form. Point slope form, y equals m times x minus x sub 1 plus y sub 1. All right, so we know our slope. When we write an equation in point slope form, all I need to know is the slope and any point on the line. So any point on the line, well, we have 2 given to us. We can go one or the other. It doesn't make a difference. All right. So this would be x minus 5 plus 2. All right. So I'm just chucking in my x and y value. This is my first coordinate. So that makes this the x sub 1. And that makes this the y sub 1. All right. This is my second coordinate, but who's to say that we're looking at it from the same perspective? If you wrote down 7,9 first and then 5,2, maybe the 7,9 is your first coordinate. Bottom line is, it doesn't matter. I could use either of the coordinates here, in which case I could also get an equivalent equation, x minus 7/2 x minus 7 plus 9. Let me get a nicer color going on here. or at least not necessarily nicer, just something that is a little bit more distinct. All right. So I can test to make sure that these equations give the same graph, and that'll, in a sense, verify that I did everything right. Now, if I ask you for slope-intercept form and you put point-slope form, yeah, you got a right equation. It just wasn't the one I was looking for. That's a different story. Yeah, so you just got to know the terminology. But the good thing about it is, and this is not always the case, but with linear functions or linear equations, the name of the thing tells you the form that it should be in. Like slope-intercept means that I should have the slope and the intercept in the form of my equation. Point slope, the slope and a point. All right. Now in NumWorks, if I want to create a graph, I hit that little home icon, all right, this one right here, and you'll see the option for grapher. All right. Now I've used this already for other classes, so it's not in the ordinary landing spot. But the thing about NumWorks is it remembers where you left off. And when you go into a menu, it brings you to the same place that you were. So you can navigate backwards or forwards from there. All right. But what I want to do is I want to get up to expressions. Well, you don't need that one. So if you want to wipe out an entire field, you just hit the backspace button. All right. That's this one over here. All right. And then add an element. I'm not too thrilled with the way they phrase that, right? Because that's like their stock way of saying this is where you type stuff. But you know, I'm going to be putting in an equation that I'm going to plot. So it'd be nice if it said add or enter an equation here or something like that. But you know, it's not perfect, right? So, but I'm going to hit OK, and when I go into this, when I hit OK, it brings me into a template. If I go down the line in here, I could find different ways that equations can be represented. It gives you a place to get started, right? So you see all these different possibilities. You know, we're actually going to touch on almost all of these before the course is over. But if I needed to put in something fairly complicated, it has a template that I can just kind of build off of, right? Maybe I want to put in this equation, but I want to put some coefficients in there as opposed to just leaving it with coefficients of 1. Or maybe I want an inequality and I don't know how that should look. NumWorks is going to help me with that. All right. But if you want to go like legit from scratch, you can type in, you know, hit OK on empty and type in what you want. All right. So you'll see in the background behind every key, there's the alpha version or the shift version. All right. So I want to bring up a Y. So I'm going to hit alpha 3, brings up the letter Y, lowercase. All right. One thing that, you know, it's not ideal, but they label the keys with uppercase, but when you hit it, it brings up lowercase. If I wanted an uppercase Y, I'd have to hit shift alpha 3 and it'll bring up uppercase. I don't want that, but just so you know. Behind the pi is an equal sign, like diagonally up from the 9. So if I hit shift pi, oops, I didn't hit shift enough. Shift pi, it brings up an equal. All right. And then I could type in whatever equation I want to type in. So I'll do my slope intercept, 7/2. The X key, you can get the X key the same way we got the Y key by hitting alpha 2. Or you see up here, you have this key. All right, the XNT key. If you hit it once, you see it cycling through different characters. That's because the key means different things at different times. All right. So if I hit it once, it brings up the X. If I hit it twice, it brings up an N, then a T, then a theta. They don't have theta written on the key, but all I want is the X. So if you need a variable, odds are this is where you're going to go. All right. Minus 15.5. And then hit OK. I could take a look at this picture and hit plot graph. Now, my window here is not really user-friendly. I can tell you it was really user-friendly for the problem I was doing in my statistics class with this, but it's not really useful right now. So I would go up to auto and select that, right? Auto, whether it's NumWorks or any other kind of calculator, it's really a simple way of saying, let the calculator figure out the window, right? I just want to see the graph. The calculator is going to figure out the best window to see that graph, all right? So I have, again, the line, we typed in y equals 7/2x minus 15.5. This most likely is it, all right? I'm not really verifying anything, but I can navigate and calculate. Right. So if I go to navigate, I can drag around left and right, up and down. And if you ever get stuck anywhere, the curly back arrow, the one right next to OK, that's your, oh, I went too far, I want to go back. All right. But I could also go to calculate and I could find things like, if you go into find, I could find the max, the min, zeros, tangents, integrals. All right, so that's more calculus stuff. But zeros, that's another way of saying intercepts, x-intercepts. All right, well, I wanted the y-intercept, so that's not as helpful. But you know, you can start playing around with certain things like this. You could also go to particular x values. If you select go to, maybe I don't want to go to 4. I know when the graph is, or when the line crosses the x-axis, I'm sorry, the y-axis, that would be the y-intercept. I know that's going to happen at negative 15.5. So 15.5 units below the x-axis is where this line is going to cross the y-axis. So if I type in a 0 here, it's going to bring me to that spot. And at the bottom, it's going to give me the corresponding y value. All right, so I just confirmed that the y-intercept for this graph is negative 15.5, which is what I suspected because that's how I built the equation. All right. I could also do it for, you could just type in numbers now and it'll overwrite the x value. If I type in a 5 and hit OK, it brings me to 5, 2. That's one of my coordinates. If I type in a 7, it brings me to 7, 9. That's another one of the coordinates. You know, but then maybe I want to go in the negative direction, negative 5. Negative 5 is what I said. You know, just to see what the y value would be for that number. Or maybe I just want to toggle along and just kind of get a sense of coordinate values that way. All right, bunch of different things you can do with it. For number 2, write the equation of the horizontal line. All right, just a little refresher. Horizontal lines have slope equal to 0. All right, so that means m is equal to 0. So if I use my point slope form, and by the way, I'm showing you these two techniques, but the preferred approach would be the point slope form. All right, the preferred method is going to be the point slope. All right, not just by me, like going down the calculus road, the calculus track. Most people, if they don't exclusively use point slope form, then they're at least using it most of the time. May not use it all the time, but they're using it most of the time. All right, so you're going to want to have pretty good, fluency in that. All right, so if I use my point slope form, again, y equals m times x minus x sub 1 plus y sub 1. And here's my x1, my x sub 1, and my y sub 1. I'm going to replace the m with a 0. X minus negative 9, although that's going to be irrelevant in a second, but it's worth mentioning. plus 2. Now this whole thing, we have a 0 factor. So that's all going to zero out, regardless of whether you put the correct amount of minus signs in there. It's going to zero out anyway, and you get the line y equals 2. All right. Vertical lines, they have the same kind of structure in terms of the final answer, but you can't substitute in no slope. I mean, you can, it's just not going to bring you anywhere useful. All right. Parallel and perpendicular lines. Again, this is all old stuff, but it comes up often enough that it's worth taking the time to review. Parallel lines have equal slopes. Perpendicular lines have slopes that are negative reciprocals. My house phone is ringing, which can only mean one thing. That Sirius wants me to subscribe, and I'm not going to do it. Sirius XM, satellite radio, all that. You know, like you get a free trial when you get a car, and then they're like, "Oh, you like this, don't you?" I'm like, "No, I don't. I don't use it." All right. So negative reciprocals. Now, just a quick refresher. For example, a negative reciprocal of 2. Well, 2 could be thought of as 2 over 1. I'll put a little over 1 here. Negative reciprocal means that you're taking the reciprocal of the fraction, but then also negating it. All right. Some people call it opposite reciprocals. It really doesn't matter what you call it as long as you do it. So negative 1/2 would be the negative reciprocal. The number 2 started off as positive. The fraction 1/2 should now be negative. Another example, let's say you start off with something that's already a fraction. Let's say negative 2/3. So negative 2/3, well, forget about the negative for a second. The fraction itself is going to be reciprocated. That's not really the right use of that word, but you get the idea. You're going to take the reciprocal of it, but then you're going to negate it also. All right. So negative becomes positive. So you don't have to put a positive sign in there, but you know, it's a fact. All right. All right. So just one more. Let's say you have, well, honestly, it really doesn't matter as long as it's positive fraction. I'll say 7/4. Flip it. And since it was positive before, it now has to be negative. So you flip the fraction, reverse the sign, and you got what you needed. All right. So for number 3, we're pulling information out of the equation of the line. Y equals negative 3x minus 4/5, this one over here, because I know I'm going to be parallel to that. So the slope of this line is going to be negative 3 because this is in the y equals mx plus b form. All right, so the m value, if we stack it up like that, the m value has to be a negative 3. All right, now that's the slope of this line, but since the new line is going to be parallel to it, the new slope is still going to be negative 3. And really, when I say new slope, I mean the slope of the new line, the line that we're trying to create. Now we know that it passes through a point. That point has coordinates negative 2, 10. So this is tailor-made for the point slope form. All right, so because this would be my x sub 1. And this would be my y sub 1. So y equals m times x minus x sub 1 plus y sub 1. I'm going to input my new slope, which is negative 3. I'm going to input my x1 and my y1. So here's my x1. I'm just going to go here. Here's my y. Oh, that moved on me. Y1 is going to go right here. All right, so x minus -2, and then a plus 10 off at the end. And then we could clean it up a little bit, but you don't have to go too crazy. You know, the double negative, we want to make that a positive. But once you have it in an appropriate form, unless you're being asked to put it in a specific form, you can just stop there. All right. So y equals -3 times x plus 2 plus 10. All right. Let me just show you really quickly how you do that on a TI-84. Just making a simple graph. So in the TI-84s, you have the y equals menu. Again, this is an emulator. It's not an exact duplicate. There's some things that are going to look a little bit different, but it's structured the same way. All right. So if I hit y equals on the TI, from there, I would just have to put the right-hand side of the equation because they already put in the y and the equals. Subscripts are just identifiers for the equation. First y equation, second y equation, third y equation. That's how subscripts work. All right. So -3. With the TI, it's something that I've never liked, and I don't think I ever will like, and I don't think anybody likes it. And if they say they like it, they're probably lying. There's a minus key, and there is a negative key. All right. So if I put a minus here instead of -3, and then type in everything else, x plus 2 plus 10, and I go to graph, well, on the handhelds, nothing, you'll get an error message. On these calculators, nothing shows up. All right. The touchscreen version of this is a little finicky. All right. So if I do this and hit graph, now I have a line. All right. Now, because it's, like I said, it's an emulator, so it's not exactly the same, and it's also touchscreen, you don't have to worry about inputting a window, if you're familiar with that, because you could just pinch zoom. You know, it's a nice feature behind the emulators that they have online. It's just, you know, like I said, you get into a calculus class and it's in person and you're sitting there, you're like, oh, I'm just gonna get my phone out to answer this question on a test, and you're like hell you are, you know, like that's cheating. You're gonna need to know how to use a handheld, but this is a good stopgap in the event that you don't want to pay the money now. You're just gonna drag it out as long as you can. At least you can get away with some of the stuff using emulators. So just going back to my numworks. I'm just going to get this out of here. So that's one way you can write the equation. Another way would be the point slope form. I'm sorry, the slope intercept form, but then you'd have to do a little distributing and cleaning things up and stuff like that. It's really not necessary. Number 4, write the equation of a line that passes through 6, -5 and is perpendicular, all right, to this line. So this line has a slope of 2/3. The new slope is going to be -3/2. All right, so let me just move this so it doesn't get confused with the page number there. So again, y equals m times x minus x sub 1 plus y sub 1. All right, so again, we're just going to grab all our relevant information here. I have my new slope that I'm going to throw in for m. And I have my coordinates that are going to go for x1 and y1. So y is going to be equal to -3/2 x minus 6 plus a -5. You don't have to write plus a negative. You can just simplify. But technically, this is what it would look like, at least behind the scenes, because the number that we're substituting in only goes in for the variable of substitution, so the x1, y1. then we implement the signs. All right. But again, if you're comfortable enough with this stuff from experience, or you just get it, then you can skip that second step and go right to this. All right. I don't need to see intermediate algebra steps. Not intermediate algebra as in like the level of difficulty of algebra. I'm talking about like second, third, like if a problem can be solved using 10 steps and you do it in 8 steps, I'm fine with that, as long as you don't skirt around the point of the question. All right. And I'll talk more about, how assessments will work and things like that as we go. But yeah, I mean, it's not an algebra course. So keep that in mind. Really, whenever you're considering how much work you need to show for a problem, just think back to the title of the course, right? Precalculus, all right? Which doesn't really tell you too much except to say, hey, it doesn't say algebra in the title. So do I need to show all the algebra? Probably not, all right? And what people will do on a test is they'll say, I submitted my test. Please let me know if I showed enough work or not. That stuff I'm fine with. All right. So that's the quote unquote quick review of linear equations. All right. So not spending a whole heck of a lot of time on that, except to kind of just cover the necessary bits and pieces that'll help us for what we're moving towards. All right, so with that in mind, we have to review quadratic equations, polynomial functions, simpler ones, and then we'll be able to dive into the pre-calc. It's all pre-calc. So quadratics, when you're solving quadratics, you can go about it a few different ways. One way would be factoring. Another would be completing the square. And you could also use quadratic formula, but you'll see in this course especially, but as you go forward into calculus, you tend to move away towards the numerical approaches to doing things. It's more analytic. And so completing the square it's a more useful skill, not the least of which in terms of reasons is because the quadratic formula is just the result of applying completing the square to a quadratic in general terms, right? So I'll just put it on the side here. If you were to solve, and I'm not going to ask you to do this, but solve ax squared plus bx plus c equals 0, the result would be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. That's what you would get if you were to solve this equation for x. All right. Now, based on the presence of the radical, you're not getting that by factoring. You'd have to do it by completing the square. All right. And there's proofs out there that justify it, but that's probably better suited for an algebra class. Here, it's more like, well, okay, so we have a quadratic formula that we could use to get answers, but do we need that? Do we want to do it that way? Probably not. All right. Now, just a quick aside, if you're looking for, I don't want to get into like programming or anything like that, but if you're looking to create a program, whether it's in a calculator or otherwise, like Python or something, that'll solve a quadratic for you, then the explicit form that you have here, the quadratic formula, would be a really useful way of doing that, right? Because when you get into programming, there isn't really, at least in the early goings, really much with intuition, right? You have to program the intuition into the program that you're generating, right? So that was just a quick aside, but yeah, I don't want to belittle the quadratic formula. There is value to it. It's just for pre-calc and calculus 1 specifically, and even parts of calculus 2, you're going to find more value out of the completing the square method. All right. But sometimes you don't need to do any of that. All right. For this one, I could just add a 4 to both sides and get x squared is equal to 4. Now, if I want to get rid of a power of 2, inverse operations are the name of the game. You know, you want to get rid of a division, apply multiplication. You want to get rid of a subtraction, apply the addition method. You know, if you want to get rid of a power of 2, take the square root. All right. So the square root of x squared, the root and the power cancel each other out. Now, the square root of 4, that's the, say, it's the most common error made in any algebra course that involves quadratics. All right. The square root of 4 is 2, but it's also -2. And there's not many calculators that are going to tell you that. And so we'd say plus or minus 2. And it does matter whether you include the positive and the negative. All right. Depending on the context, you may not want the negative, but in other contexts, you may only want the negative. And in some cases, you want both. Right. So that's probably the simplest type of quadratic situation that you could face, which is good because we like some easy problems here and there. I can tell you, you know, like I don't want to talk too much about unit tests and stuff like that tonight, but I can tell you that on any assessment, I always throw in a problem that's like, you know, like a getting you started problem, you know, like get the confidence up. So a question like this might find its way on there just to kind of get the wheels turning, you know. And I'm not, you know, there will be difficult questions on assessments, but, you know, I'm not going to go out of my way to make a question later on in the test harder because I made one really easy, right? The easy one is supposed to be the gift to get you going, get the confidence up, and then it kind of propels you the rest of the way, right? Number 2 is really, I mean, its level of difficulty is exclusively based off of your factoring ability. If you're a good factorer, then this is no problem whatsoever. If you're not, then it might take a little bit more time. All right. But this is a trinomial. And again, if we're going to factor, then it has to be factorable. If it's not factorable, then you want to be using the completing the square method. We'll get to that in a minute. All right. So in this case, I'm looking for 2 numbers that'll multiply to the positive 6. Now, this one does not have a leading coefficient other than 1. You know, we have the understood coefficient of 1. All right. What we really need, and you know, it's kind of been I'll say it's a fallacy, but it's just misleading. And like when you first learn about factoring quadratics, it's like, oh, I'm just looking for the 2 numbers that'll multiply to the last value, but add to the middle value, which is good technique, but it's really going to be derailed if you have a leading coefficient other than 1. So what we do is we look for all of the factors of the product of the first and last term, all right, coefficient specifically. So I'm going to take the 1, multiply it by the 6, and that's going to give me a 6. I want factors of 6. All right. So those factors are any numbers that will multiply to 6. Well, we already have 1 pair because that's how we got the 6 to begin with. All right. But I could be looking at, to get to a positive 6, I could be looking at 1 times 6. Could also be -1 times -6. Could be 2 times 3. could be -2 times -3. All right. So once you kind of settle on a pair that you think you like, then you plop them in there and go for it. All right. So the first two terms have to multiply to this number. All right. So looking at a 1x squared, or just x squared, if they're going to be linear factors, it would have to be x and x. All right. We factor to reduce the power in an equation. Right. So I have a power of 2. I don't want to have factors that are going to also involve a power of 2. That doesn't get us anywhere. Right. So x and x would be the way to go. You wouldn't want to do something like 1 and x squared. All right. Because I didn't accomplish anything in terms of reduction of power. All right. So then now I'm looking for any of the values that are from this list that'll add to equal the middle term. All right. So that middle term has a coefficient of -5. I'm just looking for which of these pairs will add to a -5. So if I go into my list here, I see I have a -2 and a -3. So -2, -3. Those two numbers will add to a -5, but also multiply to a +6. All right. And honestly, I mean, if I'm being completely transparent, again, it's not an algebra course. If a question asks you to solve a quadratic, it's probably not going to ask you to do it any particular way. Right. So you could also do it using a graph or a table of values. I'll show you that in a minute. But once I have my two factors, I set each of them equal to 0 and solve. Add 2 to both sides, x equals 2. Add 3 to both sides, x equals 3. Put a little or symbol in there because it's 2 or 3 that satisfy the equation, not just one or the other. All right, either one of them will get the job done. It's the mathematical use of the word or versus what everybody uses the word or for in real life. In real life, the word or makes it seem like it's a choice, and in most cases it is. But here I'm looking at it from the context of 2 or 3 will satisfy this equation. All right. I wouldn't say like 2 and 3, because that would mean I would be plugging in the 2 and the 3 simultaneously, which would just blow everything up. All right. But graphically, if I'm doing it on NumWorks, one of the things I like about NumWorks is if you have the form of an equation that you like, you can keep it in there and just edit it over and over again. In this case, I have a line, but I need a quadratic, so it's a little bit of a different story. Right. So, but they do have templates. So I go back to my template and have a look. So what I would do is graph f of x is equal to x squared minus 5x plus 6, and find the x-intercepts. And if it's something like this where the numbers are clean, it should be pretty obvious. All right, so I'll go in, add an equation, and you can see I have different templates that I can work off of. But sometimes I just want something as simple as, okay, at least put the f of x in there for me. All right, y or f of x, if it's a function, it doesn't matter what you use. But again, x, I'm going to go power of 2 here. That's the one right above the closed paren. Minus 5x again, plus 6. And then hit OK or enter. Or I'm sorry, execute. And since the numbers are clean, you could actually go into the table of values. But you could also look at the graph. You look at the graph here, it's like, that doesn't look really very nice, right? But what I can do is I could toggle my my view, select auto. Now, if you're using it to just verify that you did it algebraically and you want to verify that you did it correctly, this might be enough for you. right? Because you look at it and say, well, it looks like it's in the neighborhood of 2 and 3, so we're good, right? But you could also go into axes and manually adjust, right? So go in, instead of auto, make the minimum maximum, let's say 0. Let me turn off the auto first. So 0, let's say I want to go 0 to 5 and then confirm. All right, it'll limit my graph so that it only goes between the x values of 0 and 5. And maybe that's enough. Confirm. So here I have pretty convincing evidence that it's 2 or 3, but maybe I want to bring it a little bit closer to the x-axis. Same idea. But now I would just change my y from auto to, I'll say -1 to 1. And then confirm. So that's a pretty nice looking view. And then I could just kind of navigate around. When the x value is 2, the y value is 0. When the x value is 3, the y value is 0. That confirms the x-intercept, right? And the idea here is, and the reason why it's x-intercept, you're getting the Reader's Digest condensed version of review of algebra, college algebra, algebra 2. So x-intercepts happen on the x-axis, where the y is equal to 0. If y is equal to f of x, then f of x is equal to 0. So what we would conclude is, on the x-axis, the function f of x, which is x squared minus 5x plus 6, must be equal to 0. Donation. Phone rings. It's either Sirius Satellite or somebody asking for money. Well, I guess in both cases, it's asking for money. All right. So, and the reason I can say that x squared plus, minus 5x plus 6 is equal to 0 is because if I'm saying f of x is equal to x squared minus 5x plus 6, I'm saying f of x is equal to 0. I'm just making a direct substitution. All right. Most people are fine with, I'm just looking at the x-axis, right? That's all I need to do. Yeah, okay. I don't need the extra explanation. But some people really want the extra explanation. It's a matter of your learning style. Learning style and level of interest. You know, because you might be a visual learner, but have no interest in the thing that's being presented to you visually. You know, that changes things, the way you approach things. So number 3 at first glance doesn't look like it's quadratic or entirely quadratic. You see a power of 2 in there, but you also see a power of 3. We have a greatest common factor here, the GCF. Oh, that's not a marker. Is equal to 2. They're all even, so I could pull out a 2. I could also pull out an x. So I would have 2x multiplied by whatever you would get if you take each term of this polynomial expression and divide it by 2x. All right, so 2x to the third divided by 2x is going to be x squared. Negative 2x squared divided by 2x is going to be negative 1x, or just negative x. And negative 12x divided by 2x is going to give me a negative 6. All right. And actually, the factors that we came up with over here would still work. Because if I want factors of 6 or negative 6, it's really just going to be the same numbers, just one positive, one negative. All right. So you could factor this using, whatever technique you want, but whether it's pulling up the graph or using a list of factors, either way, you should get, we got the 2x there, x minus 3, x plus 2. Then we set each of our factors equal to 0. The name for that was the zero product property. And all that says is that if you have numbers that are being multiplied, if any one of them is 0, then the entire product is equal to 0. So I get 2x equals 0. That's poor quality 2. And x minus 3 is equal to 0. And then x plus 2 is equal to 0. And solve each one of those. X equals 0. 0 divided by anything is 0. Add a 3, so x equals 3. Subtract a 2, so x is equal to negative 2. So little or symbols, and we have our solution. 1-0 Rangers. All right. Adam Fox on the goal. Now, again, calculators are our friend. Right? In some cases, we have to kind of convince ourselves that that's true. You know, I know from experience that people have so much history doing things by hand for whatever reason that it's like, wait, I can use a calculator. I only know how to do it by hand, you know, whatever you're comfortable with. But there is a time component, you know. So if you do it with a calculator, so I'll modify this equation. It's going to be a time saver is really what I'm getting at. So I'll type in 2x to the third. That little x to the y key here, I'll delete all that now, but that's the one that you use to raise to a power. Kind of looks cool though. All right, so I don't need the parens here. Minus 2x squared minus 12x. All right, so I have all my ingredients. Hit OK to lock it in, and then I'll go to the table this time. You can look at the picture in the graph, do auto, manipulate it any way you want. I mean, you could get it pretty easily here. It looks like it crosses at -2, 0, and 3, but you could also get it from the table, just looking for any instance in which the f of x value is equal to 0. The one thing that you run into with the NumWorks calculator is that it has a default interval. So it goes from 0 to 10 by default. But maybe I have negatives as part of my answer, and this is one of those cases. What I'd want to do is set that interval, instead of going from 0 to 10, go from -10 to 10 and confirm. You'll get a lot of stuff that you don't want, but you will get plenty of things that you do want, like this -2, which wasn't there before, is here now. All right. And again, what I said before is true. NumWorks remembers your previous settings. All right. So it's going to leave it like this until you decide to change it again. All right. So you have the benefit of knowing, or at least the satisfaction of knowing, that if you make a change, it's going to hang on to that change. You're not going to have to do it again every single time. All right. Now, I wanted to take a minute or two and review completing the square. That's what I saved the last two problems for. Whether they're factorable or not relevant at this point. We're going to apply the completing the square technique. All right. As a quick review, first thing you do is you get rid of whatever the c value is. Remember, the form of a quadratic is ax squared plus bx plus c equals 0 equals f of x, doesn't matter. The expression part of it is in this form. All right. So what we're going to do is we're going to move c to the other side. Using appropriate algebraic skills. You're not going to just physically pick up the +5 and move it to the other side. I'm going to use inverse operations and subtract it off. All right, so boom, we get x squared minus 4x. I'm going to leave a little gap and then put the result on the other side of the equation. I'm not having much success making the number 5 for whatever reason. To fill in the blank, to complete this gap, what we're going to do is we're going to take the b value, whatever the b is, cut it in half and square it, and then divide by whatever the coefficient is. That's a lot to say. The simplified formula is b squared over 4a. All right, so we're going to compute this. I didn't really give myself enough room. Sorry. And add to both sides. People learn completing the square in different ways. I'm just trying to use the one that's the most streamlined. Again, because not an algebra class, we just want to get the algebra done, all right, when needed. So that computation in this case is going to be -4 squared over 4 times 1. All right, because again, that a value, there's no coefficient written there, but that means it's an assumed 1. All right. So then simplify, -4 squared is 16 over 4 is 4. That number gets added to both sides. Factor the left-hand side. Simplify the right-hand side. All right. Now, the factored form will, if you do this right, will be a perfect square trinomial. All right. To find the factors of perfect square trinomial, you write it as a binomial square. We're going to take the square root of the first term. So the square root of the first term is going to go here. We're going to take the square root of the last term, which is going to go here, and we just drag on down the middle sign. All right. So square root of x squared is x. Square root of 4 is 2. Bring on down that middle sign. And it doesn't look like it's a middle sign, but it is. There are 3 signs on the left side of the equation. We have a positive 1x squared, a minus 4x, and a positive 4. 3 signs. The middle one is the negative. All right. Right-hand side, -1. And so now we could do what we did in the first question. Take the square root of both sides. All right. So I'm going to rewrite it to make it look a little nicer, but x minus 2 squared is equal to -1. I'm going to root both sides. That's not a square root symbol. Just freehand it. On the left-hand side, the power of 2 and the radical cancel each other. You're left with just an x minus 2. On the right-hand side, you get the imaginary unit I. All right. So square root of -1 by rule . All right. But because we are applying that radical, we have to throw in the plus or minus. All right. If the radical is already there, it's the sign of whatever the thing is and whatever it says. So if I see like written down on paper, radical -1, that's assumed to be a positive radical -1. All right. But when I myself apply the radical, there is no assumption made. I have to account for both possibilities. So plus or minus I, and then add 2 to both sides. X is equal to 2 plus or minus I. All right. And that would be your final answer. And unfortunately, the only thing a calculator is going to do is verify that there are no real roots for this. All right. So if I were to graph this, it wouldn't cross the x-axis. And that's because there are always roots. They're not always real roots. These roots are in the complex plane, right? Where all the imaginary numbers live, right? So that can happen for our purposes for the most part. There are some exceptions, but for the most part, if we see an I as part of the solution, it means that there is no solution, right? But there will be a couple of instances later in the course where we actually do something with the imaginary number I, right? The last one here, again, just like number 3, if you have a coefficient that can be factored out, you might as well, right? So we don't have a variable that can be factored out, but I can factor out a GCF of -2. So -2 x squared plus 2x plus 10. And again, same idea as before. Yeah, if you could factor it, go ahead, but we're going to do completing the square. Now you might wonder what to do with that -2. Well, there's no variable attached to it. So I can divide both sides by -2 and just get rid of it. All right. So if I divide the left side by -2, it'll cancel. And on the right side, I'm dividing 0 by -2. So it just goes to 0. Can't do that if you factor out a variable. All right. So what we did up here, when we have the 2x, I wouldn't be able to just divide 0 by 2x. I'd be losing a solution. All right. But a constant multiple is not in and of itself a solution. All right. So we don't have to worry about it in this context. So x squared plus 2x plus 10 is equal to 0. Again, I'm going to get rid of that c value. I'm going to subtract it off. X squared plus 2x, leave a gap to complete the square is equal to -10. And again, I'm just going to do that b squared over 4a computation to get the value in the middle. All right, so b squared over 4a is going to become 2 squared over 4 times 1. And in both of these problems, the leading coefficient ended up being a +1. But you could see in this case, it very easily could have been a situation where we couldn't factor out the -2. If that's the case, then you'd have something other than 1 to input into this formula, right? But that's not the case in this situation, right? But here we get a 1. I'm going to add 1 to both sides. Factor the left-hand side. So again, square root of the first term goes here. Square root of the last term goes here. And we bring on down the middle sign, and that goes here. So x, a 1, and a -9. All right, then I'm going to take the square root. All right, again, I'll rewrite it like I did before. Root both sides. X plus 1. Now, this one is not as simple as just, oh, the rule is, like the square root of -1 is equal to I. Here we're going to do a little something extra, but nothing too crazy. What I'm going to do is I'm going to break this up into factors, 2 radicals, or the product of 2 radicals, one of which is a -1. All right. If there's a sign in there other than a positive sign, then this is what you want to do. All right. So we break it up into the square root of -1 times the square root of 9. Right. Radical -1 times positive 9 is going to be a -9, or radical -9. All right. And then I can look at these independently of one another. Square root of -1 by definition is I. Square root of 9 is 3. Put it together, 3i. All right. But because we chose to take the square root, we brought it upon ourselves. I'll fix that later. We have to put the plus or minus in. All right. Because the radical wasn't already there, we introduced it. We have to tack that on. And then I just bring the 1 over by subtraction, -1 from both sides. You're going to get x is equal to -1 plus or minus 3i. All right. And that would be your solution. Again, the only thing a graph is going to tell you in this context is that it doesn't cross the x-axis. And it's not going to give us enough beyond that. All right. So we would need to have, the skills to be able to handle this kind of thing independently of a graph. I just wanted to take you through like one or two graphs, before we end, because really that's the only other place we can go with quadratics, at least at this point. And
Professor,
and
can
it's
I
really
ask
not
one
that bad.
question?
Sure.
For questions 4 and 5, how come when factoring the left side, you take the square root of the first term and the third term instead of doing the so for example, for question 4, we got x minus 2 squared, or in a x minus 2 in a bubble squared, but I factored it out like x plus 1, x minus 5.
X plus one, x minus 5 wouldn't get the job done because one times -5 would give you a -5.
Okay.
So the factors that you came up with there would actually be good for this problem. Right? Because if your C value is positive, then the signs that make up your your factors, they have to be the same.
Okay.
All right. Yeah, and that's the thing when you're doing completing the square. Once you get to this step here, what we want to do is the whole point behind completing the square is to get it as a binomial squared so that we can take the square root. All right, so we're kind of forcing the action in this direction. All right, that's what we want to have as a result, so that we could use the square root, bring down the middle sign technique. All right.
Gotcha.
So that's the thing. Like you always want to keep in mind that, and this applies to anyone. Like you have different approaches that you could take to solve a problem. I'm presenting different like techniques that you would have learned in the past in the event that you may need them in the future. You may be able to do it using any methods that that have nothing to do with what I'm teaching. It's just I recommend these approaches at least from time to time. Okay. Good question. Yeah, so for number 6, we want the equation in standard form, and then we determine the vertex and the axis intercepts, and then graph it. All right, this part here, the standard form, that's the trickier part, and that's where completing the square comes into play. Well, we want it to, when we talk about standard form of a quadratic, it's in the form of f of x is equal to a times x minus h squared plus k. All right. And let me write that below it, actually. It really doesn't matter where you write it. It's just I wanted to have it here so I can make a little extra note. HK is the vertex. Vertex, turning point, maximum or minimum, they all really mean the same thing or imply the same thing. And so if we can get our equation to look like that, then we can get the vertex, we can get a lot of things. Right? We can get the orientation of it. If A is positive, it opens up. So if A is greater than 0, it's a upward facing parabola. If A is less than 0, it's a downward facing parabola. All right, so you get some good information out of this. The axis of symmetry is x equals whatever the h value is. It's going to be a vertical line at least until we get to conic sections, in which case it could be a horizontal line. All right, so what I want to do here is, again, it's completing the square. I want to apply that technique. So I'm going to do what I did before, except instead of having 0 on one side, I have an f of x. So I got to deal with that. All right, but it actually, I will say, it ends up being a little bit easier than what we were just doing. All right, because we're never going to have to take a square root, which is good. right? So I'm going to first add a 5 to both sides. So we're going to get f of x plus 5 is equal to x squared minus 4x, and then we'll have the blank to complete the square. We're going to apply the same rule that we just used to fill in the blank. All right, we're going to determine b squared over 4a. All right, so again, this is ax squared plus bx plus c. All right, so this is going to be negative 4 squared over 4 times an understood 1, which means that I'm plugging, we got 16 over 4, I'm plugging the 4 into the gap. All right, so that's a positive 4, so it's a plus 4. All right, so what I'm choosing to do is add whatever the b squared over 4a value is to the right-hand side. But I can't just add a number to one side of an equation without also adding it to the other. All right, so if I add a 4 here, I have to add a 4 on the other side. All right, so these two have to match. I already used green, so let's go back to yellow. All right, so on the left-hand side, f of x plus 9. Right-hand side, I could use my factoring shortcut, because again, this is a perfect square trinomial. PST, perfect square trinomial. That's our license to use the technique of taking the square root of the first term, putting it here. Let's get a fresh new one. Go a little purplish color there. Not so good with the colors, or at least the names of them. Oh, well, now that doesn't look anything like it. You know what? I'm going to stick with yellow. All right, so this is going to become an X. This is going to become a 2, and we're going to drag down that middle sign, so minus. All right. If you have a technique, a factoring technique that you're more comfortable with when it comes to perfect square trinomials, by all means, but this is a nice, quick, user-friendly way of doing it. So now I just want to get f of x alone. So I'm going to subtract off that 9, bring it back the other way, cancels here, and now I have an equation in standard form, specifically a quadratic equation. All right. So what do we do with this? Well, based off of the form here, I know it got a little messy. So let me, I'm just going to kind of move this off to the side a little bit. Just kind of chuck it over here. I'll find a different place to put it. I didn't want to crowding these computations. All right. But if I compare this with my standard form, f of x normally is equal to a times x minus h squared plus k. The a value must be equal to 1. The h value, this tends to trip people up a little bit. But basically, what I'm saying here is whatever this is, it must end up being this. All right, so a good way to handle that is to take -2 and set it equal to negative h. So that'll give you h equals 2. Along the same lines, I'll go orange, some kind of orange anyway. Maybe a peach. All right, these two need to be equivalent. So I would say -9 is equal to k. Well, that's the same as saying k is equal to -9. So I have my axis of symmetry, a of s, which is x equals 2, and my vertex, oops, I think my Apple pencil is dying. My vertex coordinates to -9. All right. We could also figure out things like the y-intercept. Now, the good thing about the y-intercept is, well, actually, maybe it's not the good thing about the y-intercept. The good thing about this general form of a quadratic, this one up here, whatever the c value is, c has to be the y-intercept. Because you get a y-intercept when you replace all the x values with a 0. So if I replace x with a 0 here and here, then the only thing that's going to be left over is a -5. All right. So that gives this as the y-intercept. All right. Now, if you only had the standard form to find the y-intercept, you would compute f of 0. All right. And remember, when you say f of whatever, that number is what's getting substituted in for x in your function f of x. All right. So in this case, it would be 0 minus 2 squared minus 9, which is -2 squared is 4 minus 9, so -5. So that's my y-intercept. All right. And from there, we can pretty easily come up with a graph. Now, you might remember previous classes, maybe even in like a science class, when you make a graph, got to label the x-axis with all the numbers, the y-axis and everything. Here and into calculus is more like a rough sketch. As long as you have the important values, you're good. All right. So I have axis of symmetry at 2, specifically coordinates of the vertex at 2, -9. So I'm going to make this 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where I'd have -9. 2 would be right about here. All right. I also know that there's a y-intercept at -5. All right. So the y-intercept at -5 is going to be 1, 2, 3, 4 right here. So 2, -9 coordinates of the vertex. Because the a value is 1, this must be an upward facing parabola. We also know that the axis of symmetry is equal to 2. All right, so let me just plot the axis of symmetry. It's going to be a vertical line. I make it dashed because it's not actually part of the graph. And let me just move this point over a smidge. All right, so I now know 2 points that this graph has to go through, but also the axis of symmetry is the line that the graph must be symmetric around. So you have a point here that's 2 units away. So there must be another point 2 units in the other direction. All right, you got 2 units here, you got 2 units there. That's the symmetry part of it. All right. Then ideally you'd have the x-intercepts, but we learned before sometimes they're not clean and sometimes they're not, they don't exist. All right. But if you can find them, you should. And for that, you may even want to go into the calculator. But you could also, I'll show you really quickly, just continue this idea here for the x-intercepts, set f of x equal to 0. So you could take advantage of the work that you already did. So you can make this 0 equals x minus 2 squared minus 9. Then solve for the power of 2. So I'd add 9 to both sides. So I get 9 is equal to x minus 2 squared. Take the square root of both sides, no imaginary numbers here. Square root of 9 is going to be 3 or -3, so plus or minus 3. The radical and the power of 2 cancel each other over here. And then I would add 2 to both sides. So I'd get 2 plus or minus 3 is equal to x, which gives me the or part of things, 2 plus or minus, so 2 plus 3 or 2 minus 3. So 5 or -1. So now I have a couple more coordinates that I could get on there to make the sketch of my graph. -1 would be about right here. I'm already out 4, so 1, 2, 3, 4 units. I need to go one more. And now I have points on the x-axis and a reasonable idea what the shape of the parabola should look like. So you just make a nice smooth curve going through the points that you have. And you have your parabola, which we call f of x. All right. Yeah, there's a lot going on with this one, but I don't know how to really say this. You're not going to have to do half of this stuff in any one problem. I'm just trying to get this to resize a little bit. And so why would I do it this way? Well, obviously it's to torture you, to scare you, to make you think the course is going to be really difficult. No, it's none of that. These are all skills that you need to know in this course. You're just not going to need to know all of them at the same time. You know, some problems are just going to focus on getting a function in standard form. Some of them are just going to focus on getting a vertex. Honestly, if I gave you a problem and said, here's a parabola, find the vertex, go into the calculator and find it. See where it turns around. The one I have up on my screen, it turns around, well, actually this is a cubic, but I'll put in this one, x squared minus 4x minus 5. All right, so I'll put that in there. You go into the table and look for symmetry in the y column. You know, so you'll see that in most cases, unless there's fractions involved, there will be one point in the f of x column where the values just kind of reverse themselves. All right, so we start off, we're going 7, so 7, 0, -5, -8, -9, but then back to -8, -5, 0, 7. That point where the numbers turn around on themselves, that ordered pair, that's your axis of symmetry, x equals 2, vertex 2, comma, -9, which is what we came up with over here. So I'm not saying that, you know, like I give you all this stuff here, all these techniques, that you need to know them all tonight and use them for every single problem that we do from here on out. It's more like, these are some useful skills. Let's see if we can get these skills down before too long. All right. So, you know, just kind of chunk it up. That's why I have the problems on this page where we just focused on the solutions rather than, you know, everything. All right. And so we're kind of up against it at this point. We'll talk about power functions next class. And then we'll get into polynomials and stuff like that. But this is all the quote unquote review stuff that that we're going to need to at least be comfortable with as we go forward. What I'm going to do is I'm going to put a little star on number 7. That's the problem I'm going to start off next class going over, but it would be a good idea if you took some time between now and Wednesday and gave it a shot. All right. So try this problem, and then on Wednesday we'll go over it, and then we'll continue on from there. And yeah, and that's the plan. All right. I didn't want to assign you anything more than that because I don't want to, like, there's enough for you to kind of digest. You know, so all the stuff that you know, but you need to access, and maybe some of the stuff you didn't know to begin with. All right. So take some time and review the notes, and then and try this problem, and we'll go over it on Wednesday. Not anything you need to submit. All right. I forgot to mention, I didn't do the word of the day, so I'll do that now. The word of the day is effort. Effort is the word of the day. All right. So there you go.